2.5 simplex method, we're doing minimization problems and duality. So when we're in standard minimum form, obviously we're going to minimize the objective function, and we still want the variables to be non-negative. One thing you're going to notice is the constraints are going to have a greater than or equal symbol instead of a less than or equal symbol. But here's the thing, there's a major problem with minimization is simplex doesn't work. But wait a minute, the lesson's called simplex method. How are we going to do simplex method if simplex method doesn't work? What we're going to have to do is we're going to have to change it into maximization. We're going to have to change the problem to maximize. So instead of minimizing, we're going to maximize something called the dual problem. Duality, any solution of a standard maximization problem produces the solution of an associated standard minimization problem and vice versa. Each of these associated problems is called the dual of the other. So it's kind of weird, a weird concept. We can't really do minimization. We're going to have to do maximization on a modified problem. It's going to involve something called the transpose of each matrix. And the transpose is not that hard. All you do is switch rows and columns. And what I mean by that, AT stands for transpose, is if you take that first row is going to be the first column. 2, -1, 5 would be the first column. And that second row, 680, is the second column, and the third row is the third column. That's it, transpose. So then BT, the transpose, just take your rows and turn them into columns. 1, 2, 4, 0, 2, 1, 7, 6. Two A says use the graphical method to minimize W. Graphical method, not simplex. It's saying we can graph. Remember, we can graph. We can find the minimum graphically as long as we're in 2 dimensions, and that's what we are. So I'm going to try to do this quickly because this is an old lesson. You can use Desmos if you want. I don't care. But if I was going to graph these constraints, I look at the intercepts. This intercept 9 would produce this 9, and 5 times 1.8 would be 9. So if I was doing this by hand without Desmos, I'm going to be using the intercepts method. And over here to produce this 10, y1 could be 5, and y2 could be 5 as well. So those would look like intercepts when you graph it. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I don't have to go up to 10. 1, 2, 3, 4, 5. The first one, I've got an x-intercept of 9, or a y1 intercept, I guess, and a y2 intercept of 1.8. We're going to shade above. And the other one is 1, 2, 3, 4, 5, and 5. And we're going to shade above. So that's your feasible region. Feasible region, and we see this region highlighted. We're going to need these corners. These corners. This is a review. We've already done this. This is the 0.05. This is the 0.90. This is a little bit harder to find. Algebraically, I'm going to avoid the algebra. My graph isn't awesome, but that turns out to be the 0.41. So if we were minimizing graphically, now we take those three corners and we plug them into the objective function. 8 times 0 plus 16 times 5 is 80. 8 times 4 plus 16 times 1 is 48. 8 times 9 plus 16 times 0 is 72. And remember, we're trying to minimize, so that minimum number looks like 48, right? The minimum right here, 48, minimum W equals 48 at the point 4, 1. So that's review. We should know how to do that because we did that several lessons ago. We can solve this graphically, even though I said earlier we don't know how to do this using Simplex method. Not yet, not without modifying the problem. Example 2b says use the graphical method to maximize the dual of the problem from 2a. Notice this says maximize, but this says minimize. We have to use something called the dual, and I haven't shown you how to do that yet. So I want to skip this. Let's come back to this one. Let's go to number 3 first, and then we'll come back. It says write the dual of each standard linear programming problem. So we gotta take a maximize and turn it into a minimize, or take a minimize and turn it into a maximize. That's the dual. All right, it's going to involve the transpose of a matrix. Notice on your constraints we've got a 1 and a 1 and a 2 and a 1. Look at those coefficients right there. We want to make a matrix of those coefficients. So I'm going to write kind of small, I guess. You got 1, 1, bar means equals 10. And you've got 2, 1, bar, 8. And then I want you to underline. And then your objective function goes on the bottom. And so all we're going to do is we're going to take this 2 and this 5 and put it right here, equals 0. I know it equals z in there, but we're just going to put a 0 there. So what we want to do is we want to do the transpose. So if we do the transpose, we're turning rows into columns. That top row, 1, 1, 10. The top row becomes the first column, and the second row becomes the second column, 2, 1, 8. And the third row becomes the third column, 2, 5, 0. Bar, underline. So doing that transpose allows us to write the dual problem. So remember, above the bar, that was the constraints, and below the bar was the objective function. We are now going to minimize. And this book uses Z for maximize, but it uses W for minimize. We're going to minimize. And then we're going to use the numbers underneath the bar, 10 and 8. But when we switch, we're going to use the other variable. Instead of X, we'll use Y. Y1 and Y2. That's a little bit weird. Minimize W equals 10 Y1 plus 8 Y2 subject to, and then we look at our constraints. Remember, this Y1 and Y2, so it's going to be Y1 plus 2 Y2 is greater than or equal to. I'm just looking at that top row. 1, 2, 2. And then the second row, it's going to be Y1 plus Y2 is greater than or equal 5. And then don't forget to make your variables non-zero. Y1 is greater than or equal 0. Y2 is greater than or equal 0. That's the dual. When it says state the dual, That's it. We don't have to solve it. We don't have to do anything. We just have to write the problem. So then let's go the other way. This one says to minimize, so we're going to change it to maximize. Again, we're going to start with the matrix. Look at your constraints, 3, 2, 1, bar 10. That's the first constraint. And then there's 4, 5, 0 for the y3, greater than or equal 25. And then that's all the constraints, equals 7, 5, 8, 0. Here's my setup. Do the transpose. First row becomes first column, 3, 2, 1, 10. Second row becomes second column, 4, 5, 0, 25. Third row becomes third column, 7, 5, 8, 0. Bar, underline. There's your matrix that's associated with the dual. So notice we were minimized. We're going to change that to maximize. Maximize. It was W. When we maximize, we're going to say Z. And change the variables from Y back to X. This will be X1 and X2 here. So start with the objective function, the bottom row, 10, X1 plus 25, X2. Subject to, you're going to have your top constraint, 3x1 plus 4x2 is less than or equal 7, and 2x1 plus 5x2 is less than or equal 5, and x1 is less than or equal 8. And then don't forget the non-zeros, or the make sure they're positive. X1 greater than or equal 0, X2 greater than or equal 0, X3 greater than or equal 0. There's your dual. So we need to do that in order to do problem 2b, because it said graph the dual. Use the graphical method to maximize the dual. So we got to do the same thing where we got to come up with the dual. So we've got 1, 5, bar 9, 2, 2, bar 10, and 8, 16, 0. 1, 5, 9, 2, 2, 10, 8, 16, 0. You're doing the transpose to find the dual. 1, 5, 9, 2, 2, 10, 8, 16, 0. So we can write down that dual. We were minimizing, so now we're going to be maximizing. It was W, so now it's going to be Z. Two variables, x1, x2, so you're going to have Z equal 9x1 plus 10x2. Subject to x1 plus 2x2 is less than or equal 8. 5x1 plus 2x2 is less than or equal 16. And of course, x1 and x2 are both greater than or equal 0. That's not the answer this time, because this one actually wanted me to maximize. It wanted me to draw the graph. It wanted me to maximize this graphically. So to me, if I'm doing this by hand, again, I'm looking at intercepts, and I see the first intercept would be 8 and the second one would be 4. I'm just trying to produce 8. This makes 8 and 4. 2 times 4 makes 8. 2 times 8 makes 16. 5 times, that's a little bit harder to do because it's not going to come out nice. 5 times 3.2. So if I was going to graph this, that kind of helps guide my sizing, how big I need to go. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. First one's got an 8 and a 4. Second one's got 3.2 and 8. And I'm shading down and down. So when I shade down and down, that's going to put me inside here for my feasible region. Corner points. 0, 0. This was 3.2, comma 0. This one is 0, 4. And then this one, if you've got a good picture, my picture is actually decent this time. It's going to be 2, 3. Use Desmos or use algebra to find that if you need to. So we've got those points, and we plug those points into the objective function. 9 times 0 plus 10 times 4 is 40. 9 times 0 plus 10 times 0 is 0. 9 times 3.2 plus 10 times 0 is 28.8. And 9 times 2 plus 10 times 3 is 48. Notice this time we're maximizing. We're maximizing, and that maximum number is 48. So the maximum z equals 48 at 2, 3. Now, I've talked a long time, but here's what you're supposed to notice. You're supposed to notice that maximum is 48, and it's the same thing as when we did the minimum on that previous problem. The minimum was 48. What you might notice is not the same is that 4.1. That point is not the same as the other one. It was 2, 3, but that's because we're talking about different variables here. One of them's talking about y variables and the other one's talking about x variables, but I'm not really talking about that. I'm talking about the max and the min. We minimized here, we got 48. We maximized on the next problem. We also got the 48. And that's kind of the point. The minimum is going to give you the same value as the maximum of the dual problem. So kind of to review, all of this is just saying we're switching stuff, okay? In variables, within, in constraints within, we're kind of just switching. You're switching your variables and your constraints. You're switching your coefficients from the objective function with the coefficients in the constraints. Theorem of duality, the objective function W of a minimization linear programming problem takes on a minimum value if and only if the objective function Z of the corresponding dual maximization problem takes on a maximum value. The maximum value of Z equals the minimum value of W. That's what we just showed in the graphing problem. But the lesson's on simplex. We haven't even done a simplex problem yet, right? So all of that is just to show this. The minimization is the same as the maximization of the dual. So how are we going to do this with simplex method? If it's already a maximum, you just do simplex like we've done in the last lesson. But if it's a minimum problem, you're going to have to find the dual maximization problem. So basically, in order to do a minimum by simplex, you're going to have to change it into the dual maximum. And that's going to do it for us. All right, so everything else is pretty much the same as what we've done. Solve the maximization problem using the simplex method. That's what we did in the previous lesson. Minimum value of the objective function w is the maximum value of the objective function of z. So when you do your simplex, you're going to find the maximum, but you know that's the same as the minimum of that dual. The optimum solution to the minimization problem is given by the entries in the bottom row of the columns corresponding to the slack variables, so long as the entry in the z column is equal to 1. So like your answer is going to be, look at the slack variables in that table, in that tableau. So next, this will be good practice to set up another story problem. Set up this optimization problem, but do not solve. Suppose a dog breeder needs at least 6 units per day of nutrient A and at least 3 units of nutrient B for her golden retrievers, and that the breeder can choose between 2 different feeds, feed 1 and feed 2. Find the minimum cost for the breeder if each bag of feed 1 costs $3 and provides 1 unit of nutrient A and 2 units of B, while each bag of feed 2 costs $2 and provides 3 units of nutrient A and 1 of B. I always say on these, kind of start at the end. The end tells me you're talking about number of bags of feed 1 and feed 2. We're talking about feed 1 and feed 2. So let's let that be our variables. Y1, we're talking about minimize, so we're going to do Y, is number of bags of feed 1, and Y2 is going to be number of bags of feed 2. I think that's an important first step. Just figure out what you're talking about. Figure out what your variables are talking about. I know we're talking about minimizing, so we're going to minimize. And when we minimize, we use the variable w. So how I look at this problem is I know I'm minimizing, so I go through and I try to find the numbers that I want to minimize. Okay, minimum cost. It looks like $3 and $2. So when it says feed 1, I'm going to put that first variable on it. Feed 1 costs $3. That's going to be 3y1. And feed 2 costs $2, so plus 2y2. There's my objective function. Now I've used those numbers, don't use them again. Now we have to do our constraints. Subject to. I go through and I look for where it's talking about feed 1 and feed 2. So I might have to read this thing again. I also look for the limitations on the problem. It says suppose a dog breeder needs at least 6 units. I can see right there that's going to be greater than or equal 6. So one of your constraints is going to say greater than or equal 6. I see this as at least 3. I'm thinking there's going to be one that says greater than or equal 3. So what are we talking about? At least 6 what? At least 6 units per day of nutrient A. So we got to put it in a category of nutrient A. We're looking for nutrient A. I've got feed 1 costs $3 and provides 1 unit of nutrient A, while each bag of feed 2, blah, 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 3 units of nutrient A. I'm looking at those two numbers for nutrient A with the 6. That's going to be y1 plus 3y2. It's greater than or equal 6. then I need to talk about at least 3 units of nutrient B. So find the numbers that are talking about nutrient B. It's this 2 for feed A and 1 for feed B. And then don't forget y1 is greater than or equals 0, y2 greater than or equals 0. That's your setup. That's your setup. I feel like we've done several of these story problems now. Hopefully you're getting a little bit better at them, but that's your setup. Now that we've got the setup, we should be able to minimize this, okay? Now, since there are only 2 variables, 2 dimensions, theoretically we could do this by graphing, but I want to make sure we know how to do this by simplex. That's the name of the lesson, right? Simplex method and duality. So we're going to do this one by the simplex method. However, we can't minimize. We can't minimize using the simplex method. We're going to have to change it to the maximize problem. So we're going to have to do the dual. In order to do this by simplex, we have to change it to maximize. So look at what you've got. Your constraints have a 1 and a 3. It's going to be 1, 3, bar 6, and 2, 1, bar 3. Underline your objective function says 3 and 2 and 0. We want to do the transpose to get the dual. 1, 3, 6 is your first column. 2, 1, 3, 3, 2, 0. All right. Now, I'm going to cheat here and be lazy. I don't have to actually rewrite the entire problem. I know that it's going to be a maximize problem. It was minimize. Now it's going to be maximize. I know this. It did have y variables in it. Now the dual is going to have x variables in it. Okay. But those top rows, those are my constraints, right? So those are the ones that are going to need the slack variables in it. I'm going to need a slack 1 for the first one, and I'm going to need a slack 2 for the second one. And minimize says W, so maximize is going to have a Z in it. I can see 5 variables in this problem. Without completely rewriting the whole thing, I can see there are going to be 5 variables. So I'm going to kind of cheat and shortcut a step and not rewrite it. We just did that in this problem. We just rewrote the whole problem. The first simplex tableau is going to be x1, x2, s1, s2, z. I've got 1, x1, 2, x2. I've got a slack variable. I need a slack variable to turn it into an equals. No S2, no Z, and now it's going to equal the 3 now that I've turned it into an equation. The second constraint has 3x1, 1x2. Doesn't have a S1, but it does have a S2, 0Z, and it equals 2. Now, here's you got to be smart here. Your constraint is actually Z equals 6x. Oh, I said x2 here. I meant x1. x1 plus 3x2. That's your objective function, right? But in order to put it into this simplex tableau, we got to put everything on the left side. So you still end up having to subtract this over and subtract this over. So that's not going to be 6 and 3. It's going to be -6 and -3. We want those to be negative numbers anyway. That's how that simplex method works. We're looking for the most negative, right? So if you didn't have a negative, there wouldn't be anything to do. So don't forget to put those in standard form. You're subtracting that 6 over. You're subtracting that 3 over. No slack. It does have a z in it, z equals. And then once you moved everything out of the right side, it's going to equal 0 there. There is your initial simplex tableau. And we can do the simplex method on this because now it's a maximize problem. We couldn't do it on a minimize, but we can do it on a maximize. So what do? Most negative, least positive ratio. Most negative indicator, least positive ratio. This -6 is the most negative indicator. And then you're like 3 over 1 is 3. 2 over 3 is 0.6 repeating. The least positive ratio is pointing me at this. Now remember, if I ever ask you what's the pivot element, it's the number that you've circled twice. The pivot element is the one that's stuck in the ground. That's the one that's not going to move, not going to change. The other two have to change. All right, I got to change this 1 and this -6 into zeros. And that's where I'm going to use a pivot calculator. So you got to come up with the rows and the columns. You got to come up with the rules that are going to help you do this. So let's see. I've already got the table built. 1, 2, 1, 0, 0, 3, 3, 1, 0, 1, 0, 2, -6, -3, 0, 0, 1, 0. I've already got it built. So we got to change the 1. We got to change the 1. So I'm going to change row 1. And let's see if this works. I got to change this. My rule is going to be what? 3 row 1s minus row 2. 3 row 1s minus row 2. I can do 3 row 1 minus row 2. That should work. Three row 1s. And then -1. 3 row 1s plus -1 row 2. That should do it. Okay. Changed me into a 0 here and where I want. 0 right here where I want. And then I'm going to need to change this -6. So let's change this -6. I think I can do row 3 plus 2 row 2s. Row 3 plus 2 row 2s, -6 plus 6. Yeah, that should do it. So now I'm going to change row 3. And I'm going to do 1 row 3 plus 2 row 2s. 1 row 3 plus 2 row 2s. Should do it. Okay, so 0, -1. All right. All right, so we update our matrix. Let me, let's do this. Maybe. Okay. Top row, 0, 5, 3, -1, 0, bar, 7. Middle row didn't change. 3, 1, 0, 1, 0, 2. That was our pivot row. And then bottom row, 0, -1, 0, 2, 1, 4. I've produced a new table that produces a new solution, but not the optimal solution. I don't have the maximum. As long as I see a negative indicator down here on the bottom row, I know I'm not finished yet. Okay, so what do? Most negative indicator points me here, and then least positive ratio, 7 over 5 and 2 over 1. 7 over 5 is going to be smaller, right? 7 over 5 is the least positive. 7 over 5 is, what, 1.4, and that's 2. The least positive is pointing me at this top row. Again, the one that I circled twice, that's the pivot element, that's the one that's stuck and doesn't change. The other two are going to change. So I want to change this 1. I think I can do, I don't know, 5 row 2s minus row 1. Should be able to do that. So I'm going to change row 2. And I'm going to do 5 row 2s plus -1 row 1s. Okay. Now I got to do the same thing over here. This -1, I can do, looks like 5 row 3s plus row 1. Change row 3, 5 row 3s plus 1 row 1. Just double check. 5 row 3s plus 1. That should work. Okay, I got a 0. Excellent. That's what I want, right? That's what I want. I don't have any negative numbers. That's what I want. Top row didn't change. 0, 5, 3, -1, 0, 7. Middle row 15, 0, -3, 6, 0, 3. Bottom row 0, 0, 3, 9, 5, 27. Okay. Now, we've done this before, but here's where it's different. When we're doing this dual problem, we don't find the answers the same way as what we did before. Okay. If you recall up above, it said something about as long as the z number is 1. So what I'm going to do is I want this to be a 1 right here. That was the z number, right? That number corresponded with the z number. So all I'm going to do is I'm going to just divide that row. Let's just divide that row by 5. That's one of our row operations anyway. We can divide that whole row by 5. So if I divide by 5, I'm going to get 0 and a 0 and 3/5 and 9/5 and 1 and 27/5. All right. And now we're done. Okay. So here's what's tricky. Just reading the solution is kind of tricky. To find the z, okay, z equals 27/5. We just do that the way we always do, right? This 1 is 27/5. So you can see the z equals 27/5. That feels familiar to us. But this would be S1 and S2. When we do this, it's just these two numbers. Okay? And those 3 numbers are the 3 numbers that are important. But when we have done the dual, that corresponds with your y1 value, and that's your y2 value, and that's your w value. A little bit tricky because you're not reading the solution the same way. So we had to minimize. We found our minimum w value was 27/5 at y1 equals 3/5 and y2 equals 9/5.